Okay, we've got a pretty large set of information today. The basic idea of what we're doing now, I put on this second screen here. And this is something that's been going on ever since the computers became really powerful, and that you could set up a Schrodinger system or atomic configuration analysis, or you name it, make a huge matrix that's the Hamiltonian and have the computer give you the eigensolutions, and then even give you information about transitions, spectra, that goes with that. The problem with that is that the black box that is the computer, and some of the computers were black box, so the most favorite computer was the Next. When Steve Jobs took a vacation from Apple and built a computer that was vastly superior to what was available at the time. But the idea is that you feed it a huge matrix with lots of numbers, and it gives back lots of numbers as well. But does it tell you what's going on? You see, that's the real thing that we like to do. So what we're doing in the last few days, and particularly today, is showing that you could paint a portrait of a Hamiltonian using these tensor operators, and then finding ways to plot those tensor operators. So that's really the main topic today. But there's something else we're doing today that's a little different as far as what I have been doing in the past. I've always looked for the most elegant solutions to problems that have to do with symmetry and group theory, and that elegance was based on a bottom-up approach. So we started with the group C2, and then we went to G2, and so forth. And gradually you build an edifice, and the advantage of that is that you really understand everything that's part of what you're doing. Well, today we're going to try a different way, and that is to top down. And this will go along with this project that we're doing with starting with D2. We're going to try to apply that to the octahedral group. So we're going to let the tensorial analysis give us information about what to expect of the groups that lie inside this group U2 or R3 or the two together. So you would maybe think that that's really the only way to go, since after all a big group knows everything about its insides, and the little group that if you start with a little group, well, it doesn't know anything but itself, you say. So the philosophy of this is interesting, and after we get done today, I'd appreciate your comments about which one you think you would like the best. Now, the problem with the elegant one is that it takes pages and pages to do it, and that's what I was realizing as I was writing lectures. I was sifting through a lot of things to get this to work today. Well, anyway, this business with these operators and the basic ideas of how you do group products and all of that, I think is improved by taking a top-down in some ways. Now, when we get done with this, I want to show you the applications that are really beautiful. We're going to take the applications of this that we did for the D2 symmetry and the rotor that was a simple water molecule or some object like that, and see the connection with an enormous group. The octahedral group is enormous by comparison, and symmetry is really quite daunting. Most people really don't, even though they might use parts of the octahedral symmetry, don't know anywhere near as much as there actually is inside it. So let's go ahead and get started here with just, well, we're really getting good at making or TC is getting very good at finding ways to use these black boxes to get information tabulated and in a position. But remember what we started with. we really started with something that was very small, the U2 Hamiltonian with A, B, C, and D as its parameters. And we wrote it as a linear combination of, well, A, B, and C, but really we were doing the old Pauli spinner X, Y, and Z sigma operators. Well, those operators, they are vector operators, and vector is angular momentum 1, so we're really doing a linear combination of what we're going to be working with. Irreducible, Rocca, Wigner, you name the people that did angular momentum theory, tensors. And it's the plotting of those in a rotational energy surface that's so powerful for both visualizing things, but also for computational purposes. So the U2 generators with rank 1, the vector, and then there's a scalar, that accounts for 3 plus 1, which is 4 operators that we started, basically started this course with that. And it doesn't stop there, obviously. If you're going to do something that has a 3-dimensional Hamiltonian, you're going to add to that set of a unit operator and a vector triplet. Your next addition is going to be a big one. You're going to add 5 things here. Those are the 5 components of a tensor, a rank 2 object, you see. Now, as I said, this keeps going, and you'll find tabulations of these things and discussions of these things in these references that are here. Particularly, this is the most recent one, having International Journal of Molecular Science, where we use it on SF6 problems. But I should point out that the numbers that are sitting inside all of these matrices are completely different, and I should say sometimes daunting type of coefficient. They're called Clebsch-Gordan coefficients. And what this paper has in the beginning of it is a fairly annoying discussion. Annoying because it's kind of algebraic, kind of geometric, but neither are really to my satisfaction. But I'm trying to show you how the Clebsch-Gordan coefficients, which is sort of the high level of angular momentum. There's only one other set, the Rocca coefficients that come after that. But Clebsch-Gordan coefficients are really like D functions in many ways, and they have angular momentum cones and all that kind of stuff. So there's a geometry of these things that's waiting to be explored further. We'll get a little bit into that. Now, when it comes time to actually make pictures of these things, and that's what we're doing on both these screens here, remember that this expansion starting with the scalar, working up through some components of a vector, then maybe working up on a tensor of rank 2 here, okay? And for our rotors that we've done so far, the spherical rotor wouldn't have any of those because it would only need this one right here. And that's what the SF6 molecular spectra that we're going to look at the very end of this class today comes from. And there wouldn't be any structure at all unless we've gone up to higher K. In fact, rank 4 is what we need to discuss. But rank 2 already gives us a pretty neat sort of model for the angular rotations of this. Now, unless your molecule has some rotors or gyros on board, that is, some of the vibrations start to get chiral on you. If you don't have that, then you won't be using the vectors. You won't be using rank 1 in a molecular Hamiltonian of a molecule that's isolated and rotated. Anyway, mixing all these together makes some amazing looking surfaces, and the surfaces give you information about the spectra. So that's, as I say, what we're after here is really understanding Fano, Rocca, Wigner, a bunch of people. There's some Russians involved in that too. A tensor.
Dr. Harter,
yes.
Question. So, what is meant by the 2 to the power k pole, like the pole expansions? And yeah, where do you get the poles here?
Yeah. Well, 2 to the first,
Yes, right.
dipole. That's
Oh,
this
okay, it's okay. Okay,
You see?
that-
And then you go, the next stop is the quadrupole.
oh, I'm sorry. No, I was confused.
Does that make sense?
Yeah, yeah, sure.
Yeah.
No, when I read pole, I thought you're talking about
You
poles
bring
and
up
complex
a-
analysis.
You're bringing up a nasty typo that we'll skip over, but it somehow in my book, multipole got changed into multiple.
Oh, okay.
That just means many, right? Multiple, a little bit more than just many. Okay, let's get started on looking at a question here, which, and I'll keep these two lined up so that we can compare things. The question is, what tensors go into a Hamiltonian for, say, a tetrahedral molecule? We won't be talking about CF4, but that's a favorite for some really clear spectra of what we're going to be talking about. And really not that different from the one that we'll be seeing here, which is an octahedral O molecule, 24 group elements in that group, 48 if you put the H on there, which is a horizontal reflection. So you have the same case that we did with D2. D2H gives you a little bit more information, actually twice as much, but it isn't necessarily twice as good. And the free rotor Hamiltonian that we're going to be writing here is always going to start with these dipole guys squared. Asymmetric would have 3 different coefficients here. Spherical rotor, just 1. The inertia of the rotor in all directions is the same if it doesn't distort. Now, if it doesn't have any gyros on board, we can forget this thing. Not only that, but it's odd, so it's anti-symmetric to time reversal. Well, when you have little gyros in there, well, time reversal is something you need to address, but not if you don't. This is the first, shall we say, distortion tensor operator. This is something that's modeling centrifugal distortion, and we'll explain just qualitatively how it does that. But this is certainly something that has octahedral symmetry. X, Y, and Z are all equivalent. And but you might say, well, yeah, okay, that's nice, but what else is there? What, how many of these tensors are there? So we need to discuss a little bit of algebra of these fellows to get there. So we will be rejecting this forbidden thing and just rewrite the 4th rank term in a number of different ways to get some feeling for what it has to offer. So that's what's going on here. And once again, this is top down. We're taking what we already know are the multiple functions of angular momentum 4. Okay? 2 times 4 plus 1 is 9. So there are 9 of these fellows here. This is a pretty big set of bases for the irreducible representation of angular momentum 4. But that's what we're going to deal with, both as wave functions, which these kind of are nearly that. They've had their R removed from the denominator. But the whole idea is to make pictures of these things that are useful for a molecule that has, in this case, cubic, tetrahedral, octahedral, whatever you want to call it. And I think these things actually are listed in this reference right here. And the definition of them is available in that reference. I'm not going to jump on those. You can do that on your own. But the idea that is in this old Wiley book is to invert these so that you have the simple algebraic functions exposed. And this is just 3 of the things. There's 9 things. This is inverted so that only monomials of x, y, and z are exposed. But these are all we would need to make this fellow. Okay, if we're thinking of not just x, y, and z, but jx, jy, and jz. And that's what we are interested in going into here. Okay, so that's a bit of algebra to do that.
it isn't always easy to go from top down, but there's some big steps that you take, and then it becomes, as we'll see, not so difficult. Anyway, summing all those guys up cancels a lot of this, okay? We just are left with one r to the fourth a term with a 3/5 on it. We're left with one of these guys, the x fourth rank 0 subcomponent quanta, and then finally these two get together just to make one term here. So that will be the professional way to write the Hamiltonian that this is. There is, of course, some caveats to this. When you do this sort of thing, when you go ahead and just replace x, y, and z by angular momentum x, y, and z, and then go ahead and write a fancy thing with a thick pen, a really thick pen. Okay, remember how we needed that for the oscillator? Well, we need it here too. Okay, so this fellow, this guy right here, is all set up to be shoved into the computer. All you need to do is use the Clebsch-Gordon coefficients that go with something that we'll call the Wigner-Eckart theorem. And you're off to the races with the great black box. Okay, that's the usual way to solve atomic and molecular problems nowadays. Or at least try to solve them. And the problems is that when there's high symmetry, they all these resonances, and that makes it really hard to untangle, as it were. So I would have you look back at the algebra of x, y, and z, just because it's easier to write rather than putting jx, jy, and jz, and just look at what is that you get when you do r to the fourth power, that is r squared squared, and sum them all up. Okay? So here's what you find, as you can see from just tallying these things up here. We get r to the fourth is equal to this fourth thing that we're interested in, but we get two of these. That's also octahedral symmetry. Everything up here has octahedral symmetry. This does and this does. Complete equivalence in x, y, and z. Okay? But not just being x squared plus y squared plus z squared, which is a sphere, right? This has got shape. This one has shape. This one has shape. But it's pretty much the same shape. There is only one linearly independent fourth rank octahedral tensor. And you can see that right here. This thing is just a combination of this thing with r to the fourth, with a minus sign. Okay, so we'll see that. We're going to plot these things just for the fun of it before we actually use them for spectroscopy here. But anyway, the operator version of this thing, which I would call 2, 2, or 2, 2, or something instead of 4, because that's the way the powers of the j's are arrayed, okay, is not so simply related to this guy, which is just a sum of fourth powers, since these things don't commute. That's the quantum mechanics of them, right? Now that's what the discussion in that a paper I was referring to, Journal of Molecular Science, has right in the beginning, it has an annoying discussion of this issue. But if you get through it, you'll see there's kind of some light at the end of that tunnel. In any case, what we do is we say for just doing our rotational energy surfaces, commutation is not an issue. We're just going to, that's what's going to go in a computer, so we might as well look at what it looks like. So what we do is we replace each one of these jx, jy, and jz by its fourth power by the magnitude of the operator's fourth power. Okay, we can argue about what that is later on. But anyways, there's just one fat constant here, and then all of the Euler angles, the polar angles of this object. So this is really, you know, all there is to a rotational energy surface. It's really something that's really quite simple, and we've already shown a little bit of pictures of this thing. That's what we're going to be talking about today, is this guy right here. Because that is a pretty good model for the rotation of Mr. SF6. It looks like SF6. It's the Cartesian coordinate system with the axes sticking out positive and negative equally. I can almost just put it right there and it sort of fits in there, right? That's kind of neat. And that's what rotational energy surfaces for the symmetric rotor did too. The surface is long where the actual thing is long, and it's skinny where the actual thing is skinny. And the water molecule kind of showed that, and we've mentioned enough of that, I think, as you see what's going on here. So basically what I'm doing is I'm plotting versus theta and phi, that's the internal body coordinates, body polar angles, are not alpha and beta, or phi and theta. They're beta and gamma. That's the azimuth in the body frame. So we made a fuss about that already, and now is when it pays off. And you get a surface like that. Well, what does this thing look like? What does it look like to have a minus sign in front of this thing here, you see? And so that's the plot of it. Okay? If you go ahead and just use this thing without worrying about the commutation, just plot it, well, it's going to be high where this one is low, and it's going to be low where this one is high. That's so what you get for putting a minus sign on it, right? That's really all that happened. So those are two surfaces. This one is a much better surface for things like methane molecule, tetrahedral molecule. But this one is what the doctor ordered for rotation of this thing. And the reason for that, which I'll just wave my hands a little bit to explain, is that when I am rotating around the tips of these mountains here, that means I'm doing this and I'm precessing a little bit, depending on how far down the mountain I go. But when I do that, it really doesn't distort very much because these radial bonds are so strong compared to the ones that are bending this. You see. But then if I do rotate it around this axis right here, that's rotating it as though it were a triangle. If I do that, you see, then the centrifugal force can easily spread the atoms, you see. So this thing is going to get, its inertia is going to go up because it's going to get fatter, much more so than it does here. So that's going to be the low point of the energy for this molecule. Just the opposite for a tetrahedral arrangement or a cubic arrangement. Just the opposite. Okay? So, we'll be doing this more quantitative later on. We're just doing stuff a little bit qualitative as far as the physics goes. Anyway, here's where we're going to do the top down. And we're going to start just using the dipole and vector functions of R3. That's all I want to play with. Okay, now the way they're written in this, and there's your misspelled multiple right there, okay, in the table of the book that Lewis has opened up on there. And this is way in the back. And I put Roman numeral I, or 1, for a first rank tensor, and then the second rank, which we'll get to. We'll need these guys too. This is really all we're going to need today to take care of this SS6 molecule. But I put a Roman numeral 2 for second rank. And then invert it, you see. There's 5 of these things. Well, there's really 6 of these things, but we boil it down. That's because what we're really doing when we're just talking about X, Y, and Z is we're really talking about SU3. Or not even SU3 if you don't restrict the overall magnitude of the quantities that you're dealing with here. So what we'll do is we'll be throwing out of this set here x squared plus y squared plus z squared. And that'll leave us with 5 polynomials that really do something. Okay, but let's just take the L equal 1 stuff. This is where I'm going to derive the irreducible representation called T1. And T1, it's got a good mnemonic quality. What it's referring to is T for triplet. And now I'm making this connection up, but it's still true, whether it's historically true or not. This is a triplet of this guy plus this guy plus this guy. I'm just looking at the standing waves now. I'm just looking at the real functions, the ones that have the Thales circle, sphere actually, as the amplitude. The amplitude as a function of angle here. Maximum there to 0 there as you change the polar angle on that object. It's really kind of a beautiful thing. Yeah.
So like you mentioned in that picture, it's like, for example, like I have the algebra of that molecule on top, and I have the algebra of that molecule on top, and I have the other algebra of that other. So they form like groups. They're symmetry groups. So
well, they're basis for matrix representing the symmetry group. This particular representation.
Okay, perfect. Now I ask you this question. So if I want to describe like higher, like higher symmetry molecule, like
which
molecules
we
with
will
higher
do.
symmetry,
We'll go to J equal
I can
2.
direct some of those things just to or direct product or whatever. Can I do that?
Well, we'll do that. In fact, when you go to the next stage, instead of just having x, y, and z, you're going to have x squared, y squared, z squared. The combinations of those, right? Which we just looked at, right? Those 6 or 5, depending on how you count things, right? Involving x and y, but twice. Okay, that's angle 2. That's rank 2. Does that make sense? That's where we're headed, right? And that's all we're going to need today. But we got to do it right. Okay? Is that sort of answer? You can always give. Now, this guy over here is our slide rule. Slide rule, there's a really big version of it over there, and there are littler versions sitting around here, and there's the one that you can cut out and make yourself. And I would recommend you do it there. Lewis is reaching for one right there. Okay? So this is something that lets you, and we're going to explain how this works. But those are all 24 of the operations in the group O. Now, there's some blank spaces in there that are reserved for the other half of O, which is the one that has operations that involve reflections. Those are all rotations. Every one of those is a rotation, and we're going to explain a lot about that. But mainly, right away, we're going to start off with 90-degree rotations. Rx, Ry, Rz. Big R represents a 90-degree rotation. Okay? Typical example, rotation from the identity to there is a 90-degree positive rotation around the z-axis. This is the z-axis sitting right there. Let's bring the other screen up so that it's coming in line with what we're doing here in case necessary to make a more complete picture. Okay, so this is what we're really going to work with today. It's a child's play, kind of, right? Really precocious child. Okay, so what we've got here are, and I'll go ahead just and reveal a good deal of this. These things with a little tildes on it, see, the problem was to make something that had the least amount of notation. I didn't want to have more than 3 pieces to this thing, and as soon as you put a -1 there, you get in trouble when you're making these things with lots of elements. So this is a compact representation here. That is the inverse and the third power of the original guy, RSD, and this is true for each of these dimensions x, y, and z. Okay? So I want you to note that the tilde, and you'll see them right down here, just opposite the original RZ. It's the thing that goes the other way by 90 degrees. It's the inverse of this, but it's also the third power of it if you go 1 step, 2 step, 3 step, 4 step back home. These are all, each of those triples up there belong in the cyclic group. The next one in line is a 180-degree rotation, and you see him right here. And this is all for the Z. Then over on the X side, which you see turned to the very right there, or the Y side, here, what you're looking at there are what we call coset of this original group that involves z. So we're definitely favoring the z-axis when we do this thing, and that's part of quantization, is to pick your axis for your things, you see. But anyway, the four operators, including the row, okay, which is nothing but RZ squared, but that's an extra symbol I didn't want to have to deal with, so I make up a primary symbol for that. And also, I make up the symbols in such a way to reflect the class structure of the cubic octahedral group. And we'll get more into that later here. Again, that's something that you deal with immediately if you're doing the elegant bottom-up approach to this theory. So, first thing, find some products. Let's do a couple of products of pairs of those 24 operators. And I'm picking them judiciously so each of them has a lesson of its own. Here, to calculate O products like RZ times 1, well, you already know the answer to that. R times the identity is just R. Okay, and that's true for any element in this group. But how does it show on the slide rule? Okay, well, you find the operator axis here. Okay, now that's the thing about this thing. This thing is really set up to take advantage of all of that stuff we said about the lab versus the body. This is all stuff going on with the body here. And what we're imagining is that there are operators from the outside, and that's what these little symbols over here, the little r's, little RZ here. Okay, that's what it's asking it to look for right here. The line by the small type RZ is an axis for the operation RZ. Then these guys that are plastered onto the first surface of the cube, those are representing states obtained by a particular operator. So if I do RZ times the unit operator, that means I rotate by 90 degrees. You can see I'm rotating 90 degrees there, from there to there, or from there to there. 90 degrees between this line and that line, 90 degrees between this line and that. That's a triangle, a little sector of this, well, it's a huge, funny kind of lattice is what it is. Okay, so that, as I say, that's really easy. But this is a little harder here. What's going on here? How do you do a product like that? But before I go on to that, is what I've said so far clear? I definitely want you to follow this carefully, enough that you don't have to look at it again. And anyway, that's what happened here. The state triangle number 1 is taken over by this operation to a triangle with the result written in it. That's the way this works. And it works for any element on there. Okay? There's a name, you've called these codex.
Yeah.
I mean, it's a codex. not K, but C, right? Ending in X. Okay, so let's go and do this one. What if I want to do the product of I6? Well, I6, okay? The operation that goes with that, you have to, first of all, you're writing the product, so you take the operator that's on the left and then treat this one as though it was representing a state, because that's what it will do when it's applied to the 1. The RZ times I6, okay, so I find RZ operator axis. We already did that, okay? It's right here, okay? And it's going to work on, something that's in right here, okay? It's going to rotate that thing by 90 degrees. It's 90 degrees. It's going to take this whole face and plunk it down over here. So it's going to take this thing and plunk it down over here. That's what you have to get used to. See, this is a little less easy than this, but it's still easy. Okay? So the answers are 3. That's the product. Okay? Now R3, and you can see his axis, or her axis, is right in that direction there, coming out of the board here. R3 squared is right here. That's the inverse of 120 degree rotation. On the opposite end of that, way down on the other side of everything, is where R3's axis really is, the 120 degree one. We'll get into that. R3 is 120 degree rotation around, +1, -1, -1. That's using Cartesian coordinate analysis, notation, okay? Now, what if you go the other way? What if you did I6 first, okay? And then RZ, just the opposite of this, you see. These guys do not commute. You get a completely different operator, R1 tilde. How do you see that, okay? So, once again, you find the operator axis. This is the operator, that's the victim, okay? It's aligned by a small I6, okay? Right there. There's an axis coming right out of the cube there that you have to imagine. And I'm going to grab the cube and I'm going to turn it by 180. I mean, that's the symmetry this thing has. This is on a line, so you recover the symmetry if you turn completely around by 180. So that's what that thing is. Imagine 180 rotation of I6 of the state triangle for RZ, okay, and that's the thing that's hard to see, that this is going to take you into R1, but when you just imagine spinning this little top there, and RZ lines is there, and this thing gets turned back to here, it's going to get you R tilde 1. Now R tilde 1 is a 120 degree rotation around the number 111 axis. There's R1, there's the king of all of the triangular rotations right there on the 111 direction. Remember, the z-axis coming out here, the x-axis is this line right here that's behind the scene here that goes with this plane, okay? And then the y-axis is this plane right here, perpendicular to this plane right here, y-axis, z-axis, and then there's up there you can see the x-axis, and let me get the computer's code up here so we have this stuff being shown more or less clearly. Okay, so that's your lesson in how to use a slide rule. All the other 24 squared rotations are waiting for you to try them out. Okay? All right. Now this is something we would do whether we're doing top down or bottom up, but I would say this is very much a combination of those two. Okay? We're going to have 90 degree rotations, x, y, and z, and their inverses. We're going to have 120 degree rotations and their inverses. So there are 8 of those, and that corresponds to the 8 corners of the cube. And then there are the 180 degree rotations that live, first of all, on the x, y, and z axes. They're just squares of this guy. And then there's 6 edges that have axes. Actually, there are 12 edges, but 180 degrees and minus 180 degrees for classical stuff or for boson stuff are the same. Okay, so we only have 6. They're double-sided axes. There's an I6 written there, and if you could look on the other side, there'd be an I6. There's I5 right there. It's also written right there, because that goes all the way through and comes out there. Is this giving you a headache?
No, I'm trying to understand completely. Trying to comprehend it.
Seeing as you've got one right there, can you see that might help, right?
Uh-huh.
And it takes a little practice.
So
Okay.
if I
This should be in every group theory book, mathematics or physics, right?
I mean, I have one because you asked. I asked you like I had
Right.
that cardboard thing.
Can I copy?
And some scotch tape, and you're off to the races, right? Yeah, it takes practice.
Now, incidentally,
Yeah,
we
so-
have these online, but the user interface is a little crude right now. We need to put in a free rotation operation. Right now it's set in a polar coordinate
Yeah.
realm, so you're kind of restricted to those sorts of motions.
Yeah, it's much better, I think, until we really get it fixed, to have it in your hands. Right? It's a very physical thing.
Very true.
I didn't hear, but you didn't mention anything about the diagonals, right? Like if I have like a So you have like that edge, like the one that is pointing right in front of me, right?
Yes.
Sorry,
This one
that
goes
corner.
through
I
and
said
comes to an edge on the other side.
yeah, that one I understand. But I meant the corner. So that you have.
Oh, those guys, the R,
and then you have
little
like
Rs.
the other corner exactly opposite to that one.
Yeah.
You have like those type of.
Yeah. See, if you do a 120-degree rotation around there, that's
Uh-huh.
equivalent when you're looking at it from the other side to a minus 120, right? That if it's right-handed up here, it's going to be left-handed down here, right? So
Yeah, but
this guy is the inverse of this guy.
okay, but
Yeah.
so in that
If-
case,
If I do a 120-degree rotation around that, I'm using my right hand. That's going to be
Under.
opposite direction from somebody looking down this axis. So those are separate elements. This guy and this guy are inverses of each other, just like this guy and this guy are inverses of each other.
okay, but like what I'm trying to see is like in the case of these opposite diagonals on the corners that go through the
This
corners.
guy and this guy, for example, which would be this guy here and this guy
Yeah,
down there.
exactly. You are restricted to make these rotations because you can like. So for example, if you rotate like at some
Mhm.
point, you will have like that blue face facing me. But
This
that's
guy-
not allowed, right?
This guy demands
So you have to choose
that
another
you
axis.
use your right hand
Okay,
just
there.
like you use your right hand up here.
Uh-huh.
So this represents me taking my right hand and going 120, which is a little over 90, right? Around this corner, right? This guy represents me doing the same thing. I take my right hand and I rotate by 120 around that point. That's a different rotation. In fact, it's as different as you can get. It is the inverse of each other.
You remember when he built his binary tables, sometimes he stacked up that tilde term, that inverse term, so that it was prearranged for the diagonals to be one?
So what I'm
Yeah.
saying is this.
That's a finite group.
So this
There you
is,
go.
This is the operation.
Yes,
so if
it
I
is.
rotate it 120, I will have this. That doesn't.
You have to say which finger did the 120 plus.
This one.
Okay, that's inverse to the other finger doing the same thing.
So I will have to do it. In
Those
this
are
way.
two separate elements. Yep.
So if I do like 120, right?
Around the top finger.
Then
Okay.
I gotta do like 120 with this finger.
If you do that, it'll come back home. Right? They're inverse of each other.
So so
You did it?
I'll do it in this way. So I have like this face here.
You could use the big R's just like this guy versus this guy, or
No.
this guy versus this guy, use the yellow face.
So I have this 120. This guy 120, right?
Okay, that's the
Here,
diagonal.
there it is,
There's
120. right?
different paths to map, say that
Well,
one
just remember
to
that
another target.
whatever operation
That
you
phase
do
we've
on
been
this
talking
thing,
about.
the box will be back being in the same, I mean, if you didn't have any writing on it, it'll be in the same, look the same, right? Every one of these operations here leaves the box invariant. If you can't read anything on it, if it's pure white box,
Okay.
right? There's 24 ways that are indistinguishable for that box. And the best way is to have the box sit on the table, right?
Yeah, you kind of lose
And point north.
original position.
Okay,
Right.
it makes sense because I'm gonna
Yeah.
like, so if I have like this color, if I do this, that's
Yes,
one.
There you go.
another face comes up.
If I do
There are
this,
3 ways to get a different face to come up.
so if I do 120, I have this.
Yeah, yeah,
120, I
You
do
get that?
this.
Now
and
you're
I
back
get
home
back
again.
Identity.
yeah. That's right. And the same thing's true as you go on the X, Y, and Z axes, only it's 4 times now.
Oh, but that one is easier.
Yeah.
I
Yeah.
wa-
Does that make sense?
yeah. I was just confused by
Yeah.
the corner diagonals.
Yeah.
Those
Yeah.
are a little bit more.
It's got unaligned.
And the edges too, as I say, there's 12 of these points, right? But here, this point does the same thing as the other point does, because 180 plus and minus 180 are the same rotation as far as, us living in our outside of the SU2, right? You don't have that minus sign to
So
worry
the
about.
edges are 180, right? So it makes sense because if I
Yeah.
do this, that doesn't make.
Yeah.
I
You
have
get-
to do this and then
you-
do that again and get
Right,
get
you
back.
you get one side and then you do it and you get another side and then you do it again and then you're back to the original side after just
two operations.
Wow, this is just like a
Special
rule to do
operators.
group theory. Just like I will just get this and do like the computations
Yeah,
and do
yeah.
that and do the computation and do that and do the other computation.
It works for one group, but it actually works for a number. There's a whole bunch of groups that behave like O does.
There's
We'll be talking
subgroups
about
too.
that. Yeah, we'll be
Yeah.
talking about that later.
How did you come up with this though?
Pardon?
How did you?
I just lived long enough, that's all. Finally, one day I was sitting on a crapper and oh yeah, that's the way to do group theory. You know, I mean, it's, where do you think of these things, right? Necessity is the mother of invention. Okay, this is what you deal with if you didn't have this thing, right? A table, right? Not only that, but this table has the information about the signs for the spinners. That's a whole other thing that we've already mentioned a little bit of, but we're not going to have to deal with that today. Okay, so what we're going to do here is we're going to try to make the matrix D21. And we're going to derive it just from the top down. That is, we're going to have these multiple, in this case it's just the dipole functions, that's x, y, and z. So we're just basically going to be deriving visually the effect of operations that are sitting there on x, y, and z. Okay? And remember where that is. Here is our z, and perpendicular to it is x and y. Okay? And let's keep them in sync here, just to make life easier. So this is where we do the dirty work. Okay? I look at R1. What does that do to the unit vector in the x direction? That's all we need to know. Okay? Now R1, remember, is that guy sitting on with his axis on the 1, 1, 1 direction, right middle way between the x, y, and z axes. And thus 3 axes, and it's a 120-degree rotation between each stop as you go through it like you were with the cube there. Okay? So that's the table right there. That's all we need to know. Now you just have to make a matrix out of that thing. Okay? And that's what we come up with. But you got to be careful here. And this is something that probably will change because who wants to have to do an extra transpose? But the basic idea, you see, is here, this product, R1x equal y, means, you see, that a unit, these are all unit vectors, this element, y dot R1 dot x equal 1. It means that the yx component is 1, not the xy component. That's tricky. Okay, so this is a little fly that's still in the ointment on this way of looking at things. Now, if we do this project for the Journal of Chemical Education with the first simple rotor and then this more complicated fellow here, I think we have to iron this out so we don't have this extra transpose. So I say perhaps it's better to make the array with R1x at the top of its column in an array, and then you'd get this thing directly. Okay? Didn't think of that until last night, or sometime it's way too late to do anything about it. But, okay, just remember we have to do a transpose. Okay? Now, what kind of operation are we talking about here? This isn't just multiplying two group operators. This is a similarity transform. What we're doing here is we're applying that operator R1 to Rx, sure, but you'd better do the other side because this is an operator. It's got a bunch of bras in there that need to be rotated too, the other way, inversely, than the ones that are for the ket. So we have ket bras making up this, if it's a matrix, and so we've got to have this kind of transform, victim, inverse transform. So that's the way you would actually take a rotation Rx and move it over to, well, Ry. Okay, it's just
rotating the x into y. You do it again, you'll multiply y into z, and do that again, and you'll be back home at x. So this is something that is important here. We're working on the operator axes when we do this, and not just on state triangles. It takes only one operator to handle those locations, if you will, those vectors, if you will. This is an operator we're talking about here that's getting transformed. Okay, so that's the other thing that this shows. This shows, and it's all top down because we're given this and we're going for the its properties. You see. So there's our one. Here's what happens with Rx. It leaves x alone, but it flips z with y and y with, well, -1. Okay, this is, have to look at the thing and see that it does that. Then you're ready, after you take a transpose, okay, move the minus sign is all that happens there. That's your new matrix. So we've just derived two irreducible representations, 2 down, 22 to go, of the octahedral group. Okay? Now I'm picking very selective cases here. I'm selecting operators that aren't equivalent. This operator here is equivalent to the other members of its class. Its class is all of these. They're all equivalent, okay? Belong in the same class. These guys right here, there's 8 in that class. That's a really classy class, right?
How are they equivalent again?
By the fact that if I do operator R1 inverse operator, that is actually do a rotation of a group thing, it gives me just another one of them.
In the same class.
Yeah, in the same class. It's called an equivalence relation when you take mathematics, right? Okay? So we're looking for equivalence relations. Well, there they all are, right there. These guys are all in the same class. These guys are all in the same class. And the unit element is in the same class. We got 4 of these, and we got the unit element. That's the number of classes this group has. So there's a little bit of group theory that we are rushing through there. Now, rho x, that's a 180-degree rotation around x. Okay, it turns y into minus y and z into minus z. That's pretty simple. I don't have to transpose that. So, you know, that's true, but it doesn't have any effect. And then, and these are all diagrammed here, there's this class of 180-degree rotations. Any one of them does something like that. Now this one turns x into z and z into x and y into minus y. So, well, the transposing of the ones that are in the thing is not there. So this one doesn't need to transpose either, even though it is working with stuff off the diagonal. This one's completely diagonal. Okay, now the trace of the matrices that we've just made of elements of different classes are, well, should I say different? These certainly are different, and they're different from that. But then there's 2 here that have the same trace. This will be important later on, but this is what we're really after. If you ask somebody that says they do group theory for physics, most of the time they work with these things. They don't work with these. These are messy and hard, and you need to be more sophisticated to have fun with them. But characters, anybody can work with those, and that's what we're developing right here, is a set of characters for each of the 5 classes, actually. There is one matrix that we haven't put here, and that's the unit matrix. And its trace is 3 for this particular representation, and that's why this is T for triple. The first element in the character table will be a 3 for this representation, and we'll see that soon enough here. Okay. Well, as I said, our bottom, I should say our top-down approach here has just used up all the information that you can get out of the first representation of R3, that vector dipole representation. Now we go to this one. Okay, here we use the j equal 2 quadrupole or tensor functions of R3 to, and I've already pointed at this relationship where I have 5 things here, and if I want to be nasty, I want to do the whole U3. I got 6 things there, but I'm going to ignore the sum of x squared plus y squared plus z squared. If I take that out of here, I got 5 on this side, just like I got 5 there. That will not really bother us that much. But this is what we're dealing with. We've already seen pictures of these standing waves. These are the j equal 2 standing d waves. And remember that we used 2 of those, these 2 guys right here, for our rotor analysis. Okay? We didn't bother using the other thing. But this 5 breaks very neatly into 3 things that really look the same, and then 2 things that don't quite. And you say, well, this looks the same as that. But there's a difference. These things stay away from the axes. These things love the axes, right? Oh, give me that axis there. Yum, 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 yum. I'm going to heat it up. Yum, yum, yum. Right? And this one says, I love the z-axis. Yum, 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 yum. And I also like the x and the y equally. Right? So these guys just put their charge on the axes of the symmetry. These things take their charge completely away from those axes. Well, basically, to make a long story short, what we're going to do is we're going to get to T2, another triple representation for angular momentum 2. That's this angular momentum right here, out of these 3. There they are. They're going to be x, y, z, xy, unit tensors. Very simple ones. Dyads is what they would be called. The old tensor analysis. A person would know that name. Okay? And then these 2 right here, they're made out of something that has 0 angular momentum, so it can be right on the axis. These guys are got rotation around all of the axes, so they can't be on the axis without getting the infinite energy. That's one way to look at the physics of this. Okay. But basically, we're going to be working with x squared minus y squared and 2z squared minus x squared minus y squared, which of course is a Cartesian version of the Legendre polynomial number 2, angular momentum 2. Okay. So, with these guys having no angular momentum around axes, very happy to sit on the axes without any problem. And then there's we looked at the moving wave distribution before. I won't be using that now. But we could have. We could have used it and made a completely different set of representations than we're making right now. An equivalent set, and that's important. Okay, so here's the actual moving d waves all written out, and here they are combined in such a way to make something that's completely real. These are totally all real. These the moving d waves, j equal 2. I should have said standing d waves, all real. This is a mistake. Typo. This should be standing. Okay, like this. All right. These guys down here are the moving. These are mostly complex because they got phases. Besides 0 and besides 1 and minus 1, these guys got phases too, but it's just 1 and minus 1 all they can do. That's what you mean by static standing wave. Okay. All right. Let's make use of this. And this time it's a little bit more difficult, but we don't need this anymore. I'm going to keep it there for a little while, but we don't need it because we already know what the x and the y's do. So when it comes time to do a second rank tensor, we just got to double up on this. And we got to do transpose. Okay, but it's pretty simple. T2, no problem. I look and I see that R1 takes x to y. So every one of the x's in here has got to go to a y. And then the y goes to z, so every one of the y's in here has got to go to z. Okay? And then same thing down here. Okay? R1 on z gives me x. So I just have to do that. So I write that diodes there, and I put a 1 at the transpose of this. Pretty easy, huh? We get paid for this? This is so easy.
R1 is a rotation by 120 degrees, right?
Little R1, yeah, and that's what it's doing. You see, it's taking X, sticking it at Y, right? And then it grabs Y too and puts it over at Z. And then Z's, oh no, yeah, I'm getting kicked out of my house. Where am I going to go? Well, you got to go to X, right? Now we're doing it to dyad.
You know, it looks like a puzzle to me because if I do apply again, you will shift it, and you will shift it again, and you will shift it.
That might be a nice way to look at it.
X, Y, Z, and then
Yeah.
if I shift it again, I will have like Y, Z. See, take that backwards, and you will have X at the top, Y, and Z.
Mm-hmm.
That's the way I look at it.
I think that to avoid this thing,
Uh-huh.
instead of doing it in rows, do it in columns. I think that takes care of that problem.
So you don't have, we got enough things that we have to transpose. We don't need to make more.
Okay, next stop, Rx, okay? I don't need the group table, we already used that thing to get this. Okay? So I know now that Rx is not going to move x at all, so that'll remain fixed, but I'm going to be taking y into z and z into minus y, so I got to be careful to do that. And then transpose. And the transposing here is just moving those two into each other. The one that's sitting on the diagonal is not being hurt. And then there's 180 degree around, say, the x-axis. Okay. Again, it's totally diagonal. These 180 degree rotations don't make anybody leave their home. They just have to go live in the basement on the other side of their axes. Okay. And then this guy, fun to get rid of the slide rule because we already know this one. This is anti-diagonal, but still it's easy. Okay. And the transpose just involves doing nothing because I get a minus here and a here. And actually didn't need to bring it up if I was only working with that kind of operation. But this is a hard one. Okay? We got to get this representation called E. This is a weird guy. Okay? Now what does E stand for? Elementary? No. Egalitarian? No. Eagle? I don't know. Okay? The way I look at it is I sort of make an E like that. This is going to be a two-dimensional representation. E for 2. Okay, that's pretty poor, right? But best I could come up with right on short notice, all right? Short notice being 75 years. Okay, now this operator R1 is going to hit our tensor, okay? And we're talking about this 2z squared minus x squared minus y squared. Or it's going to hit this guy right here, x squared minus y squared, okay? And already know what it does, so I just have to put them all in the right place, you see. I turn this thing into this thing right here. Brings my 2 times something, but it brings me up here so it's sitting underneath what we originally had. And so I just do a scalar product of this with this. Bingo, I've got the one component of this thing, okay? And then I do the same thing with this one, and this one, and this one, okay? Then I transpose, okay? I've got a square root of 3 over 2 over here, I've got to bring it down here, and this minus has got to go up to there. If you're savvy, you recognize immediately a rotation matrix by 120
It's
degrees.
a proper rotation.
Yeah. Cosine of 120 minus a half. Cosine minus a half. Minus the sine and plus the, right? So we really didn't need all this to get this, right? Well, you did need it because it's completely I mean, this E representation is incestuous. It has many copies of itself. A lot of elements share the same matrix. It's what's called an unfaithful representation. It's kind of like Trump. Okay, so we've got to watch out for it. Now, this operator right here, rotation by 90, that's not what you like to have when you're talking about threefoldness. But anyway, you go ahead and do the same thing with it. And lo and behold, you get a matrix that's kind of weird. It's got different term on the diagonal, and it's symmetric. That is quite strange. Okay, so at this point, you do the algebra, and then you scratch your head. Okay, and the trace of that one is 0. This one has a nice -1 trace.
Dr. Harter,
Here's 2 more to just look at real quick.
I have a question. When the determinant of one of these orthogonal matrices 1 is proper, right?
That's the name that's given to an operation that you can actually do to somebody without killing them.
And when the determinant
Improper,
is
it's
like-
improper to kill, right?
Uh-huh.
That's because if you're going to improperly reflect me, you got to take every molecule on this side of me and squish it through and put it on this side, turn my right hand into a left hand and vice versa, right? I'm not going to live through that. That's improper.
Ah.
And that's a determinant -1 tells you that's what that operator is going to do in that space. And that generalizes. But it's hard to generalize as you go to 4 dimensions, because there you can turn right into left just by flipping around that other dimension.
So
Yeah, because I confused it with the trace, though.
But
Yeah.
so there's 2.
They're both invariants. The trace and the determinant are both matrix invariants. You do a similarity transformation, do not affect those numbers.
Yeah, I read that here. Like, no matter
And you know what the other invariant quantities is
dot products.
or are?
Dot products.
No. Coefficients of the secular equation. Right? With 2 by 2, you only got two things to play with. Trace and determinant.
What? Oh.
It's the sum of the diagonal minors
Oh, yeah, you
Right,
got
right?
it. Yeah.
of
that's,
order, you name it, between n -1 and n plus 1.
Yeah, it makes
relate.
sense because of the. It
Yeah.
makes sense now because
Yes.
like when you write the secular equation, you have like the matrix terms.
Yes.
And you have like the determinant, the adjoints, the
Yes,
other
yes,
adjoints.
yes.
and
Complicated
the trace.
formula of a joint. You have to use the adjoint formula. It's way over there on the right where nobody can see it.
Yeah,
This is-
because since those are invariant under those
Mm-hmm.
transformations, then the secular equation has to be invariant, right?
When you state it with that knowledge, it's trivial that that's true. Yeah. But it's a big theorem. I think it's a very big theorem. Okay. So, yeah, these matrices are all 2 by 2, so it's pretty easy. But the 3 by 3s, they can give you some problems. Okay, so here's some more. I got a trace of -1 and a trace of 0. What we need to do here is sum us up. Here they all are. That's what we did today. We worked out these numbers in the character table for octahedron. We've done a big job here, just in, how long have we been in here? An hour and 15 minutes, roughly, okay? Done a big job, okay? Now what do we need to get this guy, A2? It's just the 3rd rank tensor, it's so stupid. It's just all 1s except for the operations that make it -1. And we always have one of these. This is called the scalar. Every group equations are satisfied by all 1s. Replace every group element with the number 1 and make a group table. It's 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, right? Trivial, right? The idea of this one doing that is not quite so trivial, but pretty trivial. But all of these things, that all of these matrices that we made obey the group multiplication table of the slide rule. That's really quite remarkable. And they had to, because they came from a group that was already put together, R3, to do exactly that. Okay, now, I'm going to bring this guy up to speed as well. There we are. Okay. And the next thing to do is, and we're going to sort of rush through this, because I want to spend more time on the physics as the last two lines of this lecture today. I want to spend on a good deal of the physics, the spectroscopy of the molecules. But we're in a situation now where we can take these characters right here and figure out, how these representations would come out of an orbital of any angular momentum, or a rotor that has any angular momentum. That is, we can figure out how the representations of R3 will reduce to these irreducible representations of the octahedral symmetry. That is a pretty big job right there. That's really what Bethe was thinking of when he invented the use of the group theory that had been developed by Weil, van der Waegen, and the names are slipping me up. Having an Alzheimer's moment. I can think of all the hundreds of people that developed group theory, and then finally Bethe makes physical use of it. That was a big step. And then Wigner did a pretty good job of that too. So here's the table of what happens from this character table when it encounters the characters of R3. Now the characters of R3, we went very quickly through the derivation of that. Remember that we got a sine x over x function. This, I call it the spectral function because it has all these oscillations corresponding to this angle of rotation, and that's all R3 cares about. R3 only cares about how much you rotate it. What direction? That's your choice. Okay? It only cares about that big theta angle and the Darboux angles. It only cares about this crank angle right here. It doesn't care what direction you've put. You do the rotation by 170 degrees with this thing. It's the same, it's equivalent to all of the other directions, a rotation around any of the other directions. So you need one parameter to specify the class structure of R3. Okay? Very unlike these finite groups here, that they demand different parameters. This one demands 5 parameters to take care of its class algebra. That's what we're really talking about. But anyway, we pick for the element R 120 degrees. Well, first of all, the do-nothing element, the identity element right here, the one whose number indicates how big the matrix is. So both of these are T for triple. This one here I said was double, the E. Okay, and then these guys are singlets. This one anti-symmetric, that one symmetric. That's the way 1s and 2s indicate that. The way they did with our D2 rotor. So anyway, this is a 120 degree rotation. That's all. That's all that you ever have with that class. Remember, every corner had a plus 120 degree rotation, and that accounted for it all. So you put 120 degrees down for this angle theta. Okay, and this is a little bit of a typo because we're taking it from that textbook. Instead of using the letter omega, I should be using for this lecture a big theta right there, there, and there. Okay. So this is in chapter 5 of the book that is sitting next to Lewis there. This is a link to this particular page here. Okay, so 120 degrees, 180 degrees for this one, but also 180 degrees for this one. Well, those are really simple. That's really simple. They just go 1 minus 1, 1 minus 1, 1 minus 1, same one here, 1 minus 1, 1 minus 1, 1 minus 1, okay? Every time you have an even number, you get a 1. Every time you have an odd number, you get a minus 1, okay? So that column and that column, really easy, all right? This one has got 4 different values that it can have. Well, not really, it's just 1 and minus 1, but it comes like this. 1, 1, and then minus 1, minus 1, then 1, 1, minus 1, minus 1, you see. So this one just repeats cycle 4. We got one left here, and that's 120, and it uses its 3 positions. 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1. So the deal is to figure out how to make these characters fit this character or this character right here, okay? You can see right away L equals 0, 1, 1, 1, 1, 1, 1 fits really nicely with A1. Okay? So L equals 0 has just one named for it, A1. That's the scalar. Okay? All right, what's next? Angular momentum 1 is next. Okay, it has a dimension of 3, 2 times J plus 1. It's not J, but L is written there. A rather poor looking L. Okay, that should be J for us. We're doing molecular stuff now. So I get 3, 0, minus 1, 1, minus 1. Do you see anything like that? Ah, right here, right here. 3, 0, minus 1, 1, minus 1. Okay, well we knew that. This is T1. So it's T1U if you use the notation we will be using later that takes OH into consideration for inversion parity. Ungerad, uneven. Gerade, even. That's poorly pronounced German. Okay, next stop, 5. Well, I don't have a 5 here, but if I sum these two, ooh, that's looking good. That's exactly what I'm seeing there. Minus 1, 1, minus 1, 1. Okay, if I sum that, minus 1, 1. And then, let's see if that's right. Minus 1, look at 108. I have to be a little bit careful because the 90 degree occurs here. But that's what you're going to get out of angular momentum 2.
Didn't we build an E and a T2?
Yeah.
So those would be the ones that
Yeah.
will occur. Yeah.
TC, you're exactly right. I was getting a wrong answer there. Now
But
I get
the
right
numbers
answer.
showed that though. So
Yeah, there's 2 minus 1 is 1, 0 minus, that's minus 1, and then 0 and 1 is 1. So, yes, thank you very much for reminding me of what we already know, that angular momentum 2 has the E. Now, almost all the solid state physics that's going on in this building is due to the splitting between the E's. Remember, those are the wave functions that love the axis. And the T2s, those are the guys that stay away from the axis. Right? And then a perovskite octahedral solid, that's the name of the game.
you're getting crosstalk between those regions,
Yep.
and it drives your split.
Yeah. Absolutely. Yeah. And that's reflected in the entire lattice. So the ET2 splitting is so important for the so-called 3-5 compounds because the D is just sitting there waiting to be affected by the outside world, which is the crystal environment. Okay, there's lots to learn from this stuff. It's physics, right? We got time here, I think, to do some of the physics. But anyway, this is where we actually say that the splitting occurs and show the levels splitting. Okay. If I apply a T2 to a, if I apply a break a field down by making some tetragonal perturbation of this thing. Forget the octahedral perturbation, which gave me the splitting between T1 and E. Now we're talking about something finer. Well, this is how they split. This is the correlations, level correlation diagram for some examples. In this case, dropping to D4, which has a subgroup of D2. Or the one that we're going to use today is something that goes 0, drops to D4, which is square symmetry as opposed to cubic symmetry, and then just dropping down somehow by rotating it. That's what rotors do. They break this into a C4 symmetry. So what we're going to be ending up here is with the designations of integers modulo 4, C4 notation that I like to use for the representations of that. And we'll be looking at a correlation table. This little table down here is sort of saying it all. It's telling us how these things break down in the end. E splits into 2, 0, 4, and 2, 4. That's E right there, 0, 4, and 2, 4. Skip the notation for D4, which we haven't studied yet. Or T1. T1 is a splitting that we all know from if we've studied Zeeman splitting. T1 is angular momentum 1. So you got angular momentum 1 with 3 levels, okay? And you apply a magnetic field to that to do this, right? And so what you're going to do is get one state that doesn't have any component in the field's direction, that won't move. Then you'll have one that's going right-handed, and it goes against the field, and this one goes with the field. So you have m equal, say, -1 down here, and then m equal +1 up here at higher energy. Turn the field around, of course, that's flipped. But the guy in the middle doesn't move. So there's your finger-waving lecture on Zeeman effect. But here's how it works out. It works out 0 mod 4, that's the one that doesn't move. Then there's a 1 mod 4 and -1 mod 4 is the same as 3 mod 4. So those two right there are the Zeeman splitters. This guy's in the middle. They go up and down. That one's still in the pickle. Now, T2 does a very similar thing, except now there's no scalar available to it. It's going to be plus and -1 mod 4, just like it is for P, but we're going to have something that has angular momentum 2 mod 4 in the middle of that split. And that's a whole different physics for that. Okay, so this is angular momentum 1, P shell. This is D. It splits too, and it does it that way. Well, that's a table we need for our rotors. That's going to tell us a heck of a lot. If you read it backwards, that's what we have to learn in the last 15 minutes or so of this class, is reading these tables backwards. That is, we're very proud to have made some discoveries by just doing that. So, it's time for the applications. And by the way, when I came in this morning, I realized that I had an E for application. I had application. And I almost thought to myself, hey, I'm going to leave it that way because we use apples for everything, right? Oh, this is an apple shop, right? So this is an application that you're looking at right here, right?
Right.
So, no, I didn't do that. I'm not brave enough. Anyway, let's go ahead, get these caught up because we're going to be comparing spectra on these different things. Let's review what we saw with the rotor. And we really went very fast through this. But that was where we had a group that was pretty simple, the D2 group. And the idea was that the angular momentum 10 here, this is J equal 10, this rotor is suffering from right now. And that's a magnitude that won't change if you don't touch it and apply a torque. But it could be in very big distress and becoming dizzy and sick to its stomach due to all of the flipping and rolling that it does, particularly if you put it near this point right here, or that point right there, right near the separatrix of these surfaces. And this surface is representing a breaking of a symmetry of a cylindrical rotor, a symmetric top, by having something that's pretty much like an oblate symmetric top with the trajectories of J in the body frame. Remember, J is stuck to the stars, but in the body frame, it looks like it's moving relative to the body frame. This one is where it behaves like an oblate top and is in a valley for the highest components, and then moves out of the valley to get close to the Separatrix, where it goes crazy, if you could get it to do that. Or more likely, you start off at the mountaintop here, and some internal friction takes your energy and reduces the energy sphere more and more and more until you get close to Separatrix. Then it really goes crazy and wastes energy very quickly and just crashes on some of these trajectories and spirals very slowly into the center. So that is the description of the death of a satellite that was sent into the air, or the vacuum, with, well, first spinning, so that it was just processing a little bit, but that already started to waste energy, and so it started processing more and more and more until finally it was just end over end. And it wasn't a total loss. It was strong enough that its antennas could still send information. Wow, 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 they could hear it, right? I mean, literally, that's what it sounded like on a radio. Wow, wow, wow. And they just programmed a program to decode, and they could use it, and that's the way the Van Allen belt was first discovered.
Oh,
After that
still got the
satellite,
signal through.
they could still do this experiment. Amazing thing. TRW. And John Van Allen was, I think he says his name is John, but anyway, he was very happy that it didn't ruin the experiment. Anyway, the idea was to look at how these representations behave. A1 is clearly a zero mod thing, but then you have to look and see just by the characters what A2 is, and it turns out it's odd. And so is B2. So the number 2s here indicate that they're odd. And then the number 1 here indicates it's even. Now that's where we're using something that's involving the x-axis. But suppose you look at not just the x-axis of this body here, that's the valley, but you go walking up to the top here and look at the z-axis, that's over here. Okay? The the 1 and the 2 are A's, and then the B's are just the opposite. And so that's a little bit screwy compared to this, but that is the way this group character table comes out. Now, this one right here, when you look on the y-axis, if you use the y-axis to determine whether you're A or B, that is whether you're even or odd, then that's a really simple thing to understand. But this one never gets used. The y-axis, you see, is right at the saddle point. Go either way, and it's very unstable. It started right here, and it exponentially creeps off, and wherever the trajectory is, and goes zip all the way over the other side. Remember the demonstration we did with that, right? So when you look at the spectrum, there's only one level in that desert. That mountaintop pass desert has only one level, A2. Now that's a very special situation where we picked J equal 10 and made the A minus B and B minus C equal. Okay, that's the most asymmetric you can make a top. And you get the level dead center. And then you get these funny clusters that split just a little bit. And so do these, but they're less and less and less until finally you're down to something that's really tiny splittings here. We're only talking about a few kilohertz when we're talking about gigahertz in between there. So it's really tiny tunneling parameter, if you will. Okay, so what I want to do is I want to compare this, and I'll leave it over there, with this. Okay. Now here's our friend, the fire plug. That's what we got by using that 4th rank tensor, consisting of a sphere plus this thing, with a little minus 3/5 J4 attached, just to make the algebra right. But there it is, x to the fourth plus y to the fourth plus z to the fourth. That's what this looks like. And there's the tensor form of it that we worked out. Okay? Now we're going to make use of that tensor form later on. That's a professional way to get the matrix elements for this. Instead of having to do j plus 4 times, or j minus plus 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 minus. There's a lot of algebra involved when you get to high powers of j, right? This eliminates that. We'll study that shortly. That's called the Wigner-Eckart theorem. Okay, so, but here's j equal 30. Same surface for j equal 88. Both of these have data of spectra. We're going to spend our time later on looking more closely at that. But what I want to do here is show you how the angular momentum cones really give us the answers for the rotor spectra when we're talking about this molecule. Right. Now remember what I said about this region right here being the region which, if I put the J around that axis, that has a tremendous effect on very weak radial bonds, so the molecule tends to flatten, not by that much, you can probably hardly see it in these types of things that we're doing, but just for, make a point, I'll flatten it. That's what would happen with J equal zillion, all right? But for J equal 30, it's a lot more than it's going to stretch in this way. So when it's doing like this, the angular momentum is in this neighborhood. And that's high energy because this thing still has a pretty big, a pretty small inertia compared to what it does when it flattens. And remember, the energy is proportional to inverse inertia, right? That's a key thing here. That's why this is a valley and that's a mountain. And then there's a weird region, just like the region we have here, the separatrix crossing right there. And very similar to that, that separatrix, as I think I showed you, is made up of two circles that have an angle between them. This being one circle and that being another circle. Those dotted lines of the separatrix, it's the same thing here. The same thing is happening here. I mean, it's really quite remarkable. There's a planar circle going through there, all the way around and coming back the other side. And then there's another one right there, and there's another one right there. There's three of them meeting.
A sphere with radius b plus that t term would be.
Yeah, because everything along that curve is the same energy. And energy is being plotted radially here, just like it is there, right?
Gotcha.
Isn't that cool? Yeah. So these are little trinkets of knowledge that took us a long time to find. Now, this figure here is to be compared to that figure there. Okay. We have here mountaintop rotation. That's this one. Okay. And by the way, the color scheme for the labeling of our representations is not too different from the coloring scheme for our A, B, C, D. Remember? A and D get red or orange colors. That's the kind of oscillation that just stops. It's a standing wave. Then a bilaterally symmetric thing is sort of orange. That was the B, right? A, D, and then B was sort of yellowish or orange, depending on what lecture note you looked in, right? The one that moves things, it makes moving waves, the C, right, for centrifugal Coriolis, current carrying chiral motion, wave motion of moving waves, is green. And this is the first one right here to actually have two dimensions so that it can make a moving wave. These guys are all standing waves at birth and will be till they die. Then, even more than green, if the traffic light, they have traffic lights like they will in the future, where if your computer is set right, you can go 1,000 miles an hour. You see a blue light, you just push a button and you go read a magazine while your car takes off 1,000 miles an hour. That's what's going to happen, right? You believe that? I've got beachfront property just outside the door here. But anyway, we can hope. Anyway, so we use blue, light blue for T2, which is a little more, and dark blue for that. Well, when those colors mix, because you make a cluster, well, this one is pretty much blue, but this gets to be a little yellow here, where you're talking about the cluster on the fourfold axis, this right here, this one, 1, 4, and 3, 4. And that's what you're doing, is you're reading this table backwards to figure out what is involved at each stage. And that's what you're doing over here. What do you get over here? And let's look at that a little bit, and I won't have to change the slides. Okay, here we go. We go A1, B2, A2, B1, A1, B2, A2, B1. They are in that order, A1, B2. Okay, and we're talking about rotating here around the high side, the mountain of the asymmetric top. Okay, we're talking about this guy over here. Okay, A1, B2, A2, B1. See that? That's the correlation that's going on for that kind of rotation around the long axis. This kind, this kind, this kind, okay? Where the thing is in the high energy configuration of rotation, okay? And this is the correlation table reflecting that, all right? Well, the high energy one over here corresponds to this correlation right here. So what we're going to see is A1 E. Okay. So one of the things I want to close on here, besides the color schemes and all that, is this. This is where the uncertainty works. Now, the topography of the rotational energy surface, pretty simple for this asymmetric rotor. This Symmetryx is 45 degrees from there, but it's at the other end of that trajectory, it's more like 90 degrees. So this is this is the most extreme sort of bending that the orbits of the J vector have in the body frame. By comparison, the SF6 rotor, octahedral rotor, is sort of well behaved. And pretty much all of these things right here, not very bad circles. They don't get really bent much, even as they sit down on top of the Symmetryx. And the Symmetryx for the top, the mountains, is 35.3 degrees from top to the closest approach to the Symmetryx. So it's interesting to go ahead and figure out what the angle is that we're dealing with here for the angular momentum cones of J equal 30, which is what we have in this picture. And the J equal 30, K equal 30 is very small angle, 10 degrees, 10.3 degrees. So that's what we're talking about right there as a polar angle. It's about 20.6 degrees between my fingers. And then 18 degrees for the next one, and then 23.3 degrees for the next one, and so forth. And you don't get down to 35.3 degrees until really about there. There's 34.9 right there, and then after that, it's 30.38 degrees is bigger than the 35 here. Okay. Well, that means that we've got stable precession paths for 1, 2, 3, 4, 5, 6 of the cones. So the fourfold cones go 1, 2, 3, 4, 5, 6. It's already starting to come apart right there. You can see that it's got a big splitting there, and then after that it's Separatrix time. Right. Now the threefold axis is much more restrictive. The distance from the lowest valley point to the Separatrix is only 20 degrees, 19.5 degrees, okay? And you're done after 2 levels here. This one is already over the line, okay? So when we look for C3 clusters, okay, and the mixing that you get for C3 clusters, the coloring scheme that you get for that, okay, when you mix a bunch of A's with reddish orange with a bunch of T's that have blue, you get a nice purple, a nice magenta, okay? And that's what you're seeing right at the bottom, okay, because 30 is 0 mod 3. Then you see 2 cyan, which are mixtures of T1, E, and T2. That's kind of a cyan color, a mixture of blue and green. And then the last one is right on the Separatrix, okay? Well, it's broken up. But you get these huge clusters here that involve 8 levels. Each one of these involves 8 levels. Triplet plus doublet plus triplet, 2 triplets plus 2 singlets, that's both 8. Then every one of these is 6. 6 for the 6 mountains. So this is a spectrum that, you know, really begs to be looked at. And any spherical top, particularly C60, is going to have stuff like this, much more than this, much more. The symmetry is enormous compared to octahedral, but this octahedral is enormous compared to the rotor, the asymmetric rotor. So that's why I'm so excited about going ahead with either the, I mean, it isn't just SF6 or CF4. There's tetrafluorosilane right there. There's cubane. And I shouldn't probably say that, but that is an explosive. And it's not one that has nitrogen in it, so it could get through the detectors. This is SIF4, tetrafluorosilane. And you can see it's fitting. I mean, the actual spectra is drawn there on top of the thing. This is literally lifted from the thing and laid down on the calculations to come. Just with this accuracy, just using that sort of argument for that, okay? And we're all looking in the neighborhood of where you have angular momentum of 30. It's really a beautiful fit. Even without doing the Wigner-Eckart theorem, okay? Obviously that's what you want to do if you want precision, to the kind of precision that we're going to need for C60. Okay, any questions about this? It's a bunch of algebra, and we've got some beautiful results that fit with that algebra in a very visceral way. And I think there's more to come. But at some point we do have to do a bottom-up look at the symmetry groups, the finite ones. They really need that. That's what's been lacking from group theory, among other things. Okay.
So what we plan to discuss on Wednesday, Dr.
Say again?
What we plan to discuss on Wednesday, is it a continuation of this one, or on Wednesday, or is it a...
I haven't decided yet. My feeling is that we ought to hit the finites while we're still fresh, and we can, you know, refer back to this. You know, we can play the two against the bottom up versus top down. That is something we've never tried before. So.
And he mentioned it before, but not today, about the method of Frobenius,
Yeah.
the Reciprocity Theorem. That's integral.
Yes,
Just
we
keep
need.
it in
That's the
mind.
other thing that comes out of a bottom up.
It's a joint.
How can I get away with reading tables backwards? That's the Frobenius reciprocity theorem right there. I'm glad you mentioned that.